Okay, this paper 2 has 33 marks worth of kinematics. Variant 2.2. Okay, so, and because I got a paper 5 review, so I need to readjust my brain to talk about paper 5. Okay, live. Kinematics mechanics in this variant has 33 marks. It's beautiful or not sure. But this one is easy. Scalar and vectors. Take vector, scalar, scalar, vector. Okay, next. Nothing to say, right? This one you should know. So a train moving along a straight section of a track shows a variation with time t, distance moved by the train. Describe qualitatively the motion. So qualitative here means you should use words like increase, decrease, or constant, as per usual. The motion of the train between t equal to 0 to t is equal to 1. So at t is equal to 1, you can see the gradient is decreasing. So if the gradient is decreasing, just describe. It's not state and explain, it's describe. So no need to provide evidence. So you could say that so whenever they talk about motion, think about velocity. So velocity decreases. If it is a state and explain question, then you can say because the gradient of the graph decreases. This is a pretty standard IG question, right? For a time interval from here to here. Okay, next part. Determine the speed of the train at 2 seconds. Well, 2 seconds is thankfully a straight line. So I guess we can find the gradient, and I didn't crop it exceptionally well, but I guess it doesn't really matter. So I'm going to start with 1.5 and end with 3. And then this one is 0.2. And this is 0.56. Okay, so I'll look for the gradient. So 2 marks, I must state my intent. Speed is equal to gradient of the graph. And the gradient here will be 0.56 minus 0.20 divided by 3.0 minus 1.5. That would give me 0.24 meter per second. Easy collapse. Moving on. Straight section of a track is the track, not a trap, is a part of the loop. Okay, the train completes 1 lap of the loop. So 转一个圈, turn 1 round and come back. Average velocity. State and explain. We'll say that the displacement of the track or the train is 0 in a single lap. You move 1 lap, displacement of the train is 0. If the displacement of the train is 0, hence average velocity is also 0. Okay, 1 mark. You need both points. Displacement 0, average velocity 0. Yay! Easy kill. Not easy kill. 1, 2, 3, 4, 5, 6, 7. Yes, 7 out of 7. Very nice. 2A. Cylinder is suspended from one end of a string. Okay. String is stationary in water. So I see stationary, immediately I think of net force as 0. Equilibrium ma. Okay, cylinder has a weight of 0.84 Newton. Okay, better quickly draw this. 0.84 Newton. The height is h. The diameter is 0.031. The density of water is this. The pressure difference is that. Calculate the height of the cylinder. Okay, so this is water density, not the cylinder density. So you cannot use the density equation to find anything that has to do with the cylinder's dimensions. Okay, so to find the height of the cylinder, you can say the pressure difference. What contributes to the pressure difference is the height difference of the cylinder. Okay, so the pressure difference is actually equal to rho g height difference of the cylinder. This is your height difference here to here. So, and now this one, we can use the density of water because this pressure difference is due to water. is the pressure of the water. So we can use density of water. So we can use 1.0 times 10 to the power of 3. And we can substitute the rest, 9.81. We're looking for the height difference. You can put H lah if you want. Then your pressure is 520 Pascal. And you press calculator, that will get you 0.053. Okay, so we are looking for whether there's delta or no delta, doesn't matter. C1 here, this equation, and this calculation, finally leading to this answer. Show that the upthrust acting on the cylinder is 0.39 Newton. Okay, let's go and stare at the cylinder for a bit. There is obviously some form of tension in the string, but I don't know the tension, so I don't think I can use the net force equation, because TBH, the net force equation will look like this, right? You have tension here, tension, and then you have some form of upthrust here, because obviously there's water displaced and all that. So T plus upthrust is equal to 0.84. But I don't have T, so I cannot use this equation. But what I have is the pressure difference. So what I could do is the upthrust force is equal to the pressure difference times area. Because this upthrust is due to pressure difference in the water. Okay, so we got the pressure difference, which is 520, and we have the area, don't we? What is the area? Oh, we got the diameter, 0.031. So pi d square, 0.031 square over 4. I'm using the equation A is pi d square over 4. Okay, press calculator. I will get 0.39 Newton. Yep. Next, calculate tension. Ooh, they read my mind. So the tension plus the upthrust was equal to 0.84. There. Tension plus upthrust is 0.84. Okay, so to find tension, I will take 0.84 minus 0.39, which is the buoyancy that the water provides. And that will allow me to come up with the answer of 0.45. 2SF is fine. Don't worry about it. Okay, whoa, things get exciting now. The string is now used to move the cylinder in A vertically upwards through the water. So I'm going to pull the cylinder upwards. The variation with time t of the velocity in the cylinder is shown. So, well, the cylinder is going to move faster and faster, and then slow down and stop again. Okay. Determine the acceleration of the cylinder. For the second time, you need to find the gradient of the graph, because acceleration is gradient of the VT graph. And this is the VT graph. Check unit. Ooh, meter per second square. Ooh, cm per second. I gotta convert later. Great. So from t equal to 2 is here. So I need to find the gradient of this line. This line. I guess I'm just going to take I'm going to take 0, 0 as one of my points, and I'll take this point here, which is 2.5 and 10. Okay, so 10 divided by 2.5. I guess you can minus 0 if you want it to look like a gradient calculation. But this 10 is cm per second. So whatever answer I got right, this is 4.0 cm per second per second. I need to convert this to meter per second. Okay, so centi is 10 to the negative 2. So 4.0 times 10 to the power of negative 2 meter per second square. This one should be relatively easy because the centi is not, there's no power. It's just 1 unit of distance. So 4.0 times 10 to the power of negative 2, or 0.04. Yeah. Make sure you write in 2SF. Okay, what cannot write? You write like that. Wrong. You write like that. Wrong. Wrong. Because 1SF cannot. Hello cannot. So you write this, or I guess you could write like that. Yeah, can. Okay. Okay, so if you mention that you're looking for gradient, you find gradient correctly. If mention you're looking for gradient is 1 mark liao. You look for gradient correctly, including the correct prefix is your A1. These two cannot, this one can. Okay. The top face of the cylinder is at a depth of 0.32 meter below the surface of the water at t equals 0. Okay. Use figure 2.2 to determine the depth of the top face. Okay, I'm going to draw. Okay, this is the depth. This is the water container. This is my beautiful cylinder. It is at a depth of 0.32 meter. Okay. Then eventually at this one t equal to 0 second. Then at t equal to 4 second, I want to find this depth d. I guess I just got to ask myself, between these two times, what is the distance traveled as? 4 seconds. Okay, look at my graph. 4 seconds is here. So to find distance, I'll find the area under this triangle, right? So I will just say distance or displacement. Displacement of cylinder is equal to area of your VT graph. Announce my intent. Half, height is 2.5, I think, is it? No, height is 10, base is 4. Okay. Half times 10 times 4. This, by the way, is 20 cm. Because this 10 is cm per second, the y-axis is cm per second, and the 4 is in second. So the second cancel off is cm. 0.20 meter. This is S. So hence, the depth D will be 0.32 minus 0.20, which is 0.12 meter. Okay. You can find 0.20 correctly. You get C1. You remember to minus them. Getting this answer is A1. Okay, next. Now, after playing with the cylinder by pulling it up, I release from the string after t equal to 4. So if I release from the string at t equal to 4, two things is happening here. Release from the string now, tension equal to 0. There's no more tension in my cylinder. So when I draw the forces, I don't have to think about this tension. No more this tension already. So obviously, up thrust is not enough to balance because up thrust is fixed, ma. The dimensions of the height is the same. Nothing changed here. So the up thrust is constant. So if up thrust is constant, 0.39 is constant, and tension is no longer there. So 0.39 cannot offset 0.84. The cylinder will begin to fall down. Okay. So few information, tension T equal to 0. And because of this, your net force is not equal to 0. And because of this, the cylinder will begin to accelerate. State and name the force that acts on the cylinder when it is moving, that does not act on the cylinder when it is stationary. This is such a big clue. Moving, got. Does not act when it's stationary. Drag force or viscous force or air. Can't be air resistance because it's falling through a liquid. Water resistance. Viscous force is better because that's the word commonly seen in your syllabus. Okay. State and explain the variation, if any, on the acceleration of the cylinder. Oh, this is our famous non-uniform motion question. Okay, so this is one where, okay, So when this one is falling, right, velocity increase. So say it's falling down here, V increase. So viscous force, I'm just going to call this D lah. Okay, it's our good old drag force lah. Drag force increase. So drag force will be acting in this direction. Mg minus upthrust will be in this direction. Okay, so what I'll say is just as the cylinder fall, viscous force increases with the velocity of the cylinder. Hence, your net force decreases. And because of this, link back to acceleration. So whenever they ask you to explain acceleration, always think about forces. Okay, in fact, they already hint that you should use forces here. So hence the net force decreases, acceleration decreases. Okay. All right, this is the whole question for another 7 marks. So this one is very classic. You will see it everywhere. Later I'll provide some suggestion on where it is lah. Okay, next, a spring is fixed on one end and is compressed by applying a force on the other end. Variation of the force on the spring. Hang on, I should probably do it now before it loses. I lost track. Can give you one now. If you want to try something that shows this drag force, but not in water, this one is in air. ON20 paper 23 question 3. Okay. It's not very often one. You look at the recent years, almost every year one variant will ask. Okay, so we got a spring fixed at one end, compressed by applying a force on the other end. Okay, sure. So it's a bit like this. I have a spring, and then I apply a force, compress the spring. Okay, great. The variation of force acting on the spring with its compression is shown. Okay. So if I apply a force, and let's say this is my original spring, here to here is my X. Sure. The spring has a spring constant of 800. Determine, this one, F equal Kx, our good old Hooke's law. So F1, do we have the spring constant? Yes, 800, sorry. F1 is when the extension is 0.045. So substitute 0.045. So we can take 800 multiplied by 0.045. That will give you 36. V, not bad. Easy 2 marks. You write F equal to Kx, you get 1. Answer. This one no need to think so much, okay? For the compression 0.045, elastic potential energy is 0.81. Show. Well, elastic potential energy is area under the graph. You can just write this as half Fx. You have F is 36. You have X, which is 0.045. So this should be 0.81. Okay, other options could be half Kx squared or area under graph, as mentioned just now in the first hour of this long video. Okay. So a child toy uses the spring in A to launch a ball of mass 0.020 kg vertically up in the air. Well, obviously I didn't draw my spring correctly. Never mind, I can draw it again. Ding, ding. Okay, so basically they're saying that this is my spring. And then I compress my spring. And then I put a ball here. Okay, this is the mass of the ball vertically into the air. Okay, and the compression compression of my spring from here to here is your 0.045 meter. The spring is then released to launch the ball. The kinetic energy of the ball as it leaves the toy is 0.72 joule. The toy converts elastic potential energy of the spring into kinetic energy of the ball. Use the information in A2. What was A2 again? Oh, elastic potential energy stored. To calculate the percentage efficiency of this conversion. So I have 0.81 potential energy and only 0.72 became kinetic energy. That is your efficiency. So percentage efficiency is null lah, okay? Null. But they want 100 percentage, so you multiply by 100 lor. 89%. Why? Yeah, the spring will rattle, you know, not everything is perfect. The ball, when it leaves, may have its own oscillation or small minor compression or vibration. Okay, doesn't matter. Determine the initial momentum of the ball as it leaves the toy. We know the kinetic energy of the ball, right? Kinetic energy is 0.72 joule. From kinetic energy, we can go back. Remember, the interlink, the interchange, the KL central for these topics is velocity. From velocity, we can find momentum. Okay, so half mv square is 0.72. Do we have the mass of the ball? Yes, we do. Scroll up there, 0.020. 0.020. V square is 0.72. Okay, so from here, you can find your V, which is 0.72 times 2 divided by 0.020 square root. I know it's 6 root 2, but I'm just going to do what physics normally do, which is to round this to 8.49. If you want to, 8.5 also can. All right. So momentum is 0.020 times 8.5. This would be 0.17 Newton second. Okay. So if they see half mv square, they give C1 mark. If they see P is mv, they give C1 mark. So nice, if you get the answer and your substitution teacher understand, by teacher I mean the examiner lah. If the examiner understand, then you are okay, good to go. But please show working. Okay, so all this working is strangely A1. So you can see certain parts, right? They give they join the working with the answer mark. That way, if you write the correct equation, you will get the mark, even though you may have think too much or don't think enough and then substitute the wrong value or misunderstand the scenario. At least you know the equation. Trying to help lah. Okay, anyway, the ball in B just now with kinetic energy 0.72 joule leaves point A and move vertically upwards through air. Point B is the position of the ball where it's at maximum height h above point A. Okay, the gravitational potential energy increase. You see, these are all changes increased by 0.60 joule. So the change in GPE, I guess, or EP is equal to mg, change in height, or h. So if I increase by 0.60 and my mass is 0.020, 9.81 h, I can find h. Yes, you can. H will be 3.1. Of course, you're going to ask me, Miss, where did the 0.12 joule go? Friction. Blame friction. Okay? It's always friction's fault. Nah, they even tell you average force due to air resistance. Okay. So if you think about it, you have 0.72 joule of kinetic energy here. But your potential energy, let's say this is your reference point. So we need a reference number. Let's say this is your GPE is 0. When you reach here, your GPE is 0.60, but it is maximum height. So your KE is 0. Macam tak tally, you see? 0.72 and 0 plus 0 is not the same as 0.60 plus 0. 0.12 is missing. So 0.12 joule is lost to air resistance or friction. Okay? So I'm just going to write the conservation of energy here just to satisfy myself. The change in kinetic energy is equal to the change in potential energy plus energy lost to friction or work done against your air resistance. So this is 0.72, this is 0.60, this is friction times the distance traveled, which is h. So 0.12 is F times 3.1. Then you can get your F as 0.039. Okay? When there is air resistance, the ball takes time t to move from A to B. State and explain whether the time taken for the ball to move from A to its maximum height will be more than or less than t if there is no air resistance. If there's no air resistance, your ball moving up, you see, when your ball is moving up, because this scenario, your ball is traveling up. Okay, so when your ball is moving up, what are the forces trying to slow the ball down when it reaches maximum height? There's obviously mg, our steady friend, and then there's also air resistance, Fr. If you don't have air resistance, your downward net force will be less. So if your downward net force is less, the acceleration is less, and then it will take a longer time. Okay, so from here you could say the downward resultant force on the ball is less because you don't have this air resistance to help you as the ball is traveling upwards. When the ball is traveling upwards, there are two things that are trying to slow it down. Weight, obviously, and also air resistance. But if you take away air resistance, then there's only weight. So the downward resultant force on the ball is less. So time taken is more than t. Okay? Alternative scenario. Let's say the ball is falling down. If the ball is falling down, mg is here, but air resistance is up here. Then the time, let's say the time taken to travel the same distance will be more. So in this case, acceleration increases due to Fr. You remove Fr, acceleration decrease. In this case, acceleration decreases also due to Fr. You remove Fr, acceleration will increase. Okay, so please be mindful that Fr, or the air resistance, is the cheeky trickster force that has a different effect depending on the situation. Okay, at most it's a 2 to 3 mark explanation. Even if you don't know this part, it is not the end of the world, but they will definitely ask. So if you know, that will be great. Okay, last one. A rigid plank is used to make a ramp between two different horizontal levels of the ground. Okay, this is very similar to the fishing rod question. You can look at the direction of forces, it's almost identical. I'll show you the fishing rod question very quickly. Actually, I can just think. So normally if you do variance, right, they will try to make the variance comparable, kind of, but not really. You can see they are more or less the same. Okay, so they have different dimensions. I'm going to just throw this away because it's not really relevant, just to compare. Okay, so this is a ramp. Okay, point A is at one end, so resting, you have these three forces. Okay, so a rigid plank is used to make a ramp between two different horizontal levels on the ground. As shown at figure 4.1, this is a very steep ramp, but okay. Point A is one end of the plank that rests on the lower level of the ground. A force acts on and is perpendicular to the plank at point B. The plank is held in equilibrium by a rope that connects point D to the ground. The plank has a weight of 96 Newton that may be considered to act from the middle, which is the center of gravity. If they say center of gravity, means it's the middle. Okay, sure. Rope is perpendicular and has a tension T. Plank is an angle of 38 degrees to the vertical. Forces are all shown. Component of weight that is perpendicular to the plank. Okay, same story. We're going to split this so that it's 90 degrees. And another component is parallel to the plank. So it will have no moment about the point A or point B. Okay, so here, this one will be 96. No, it is opposite the angle 30. So sine 38. Opposite angle, we will take sine. Okay, so just 96 sine 38 is 59. Okay. Taking moments about A, calculate the tension T. Okay, boss. So we're going to take moments about A to find tension T. Same thing, lor. Clockwise is equal to the sum of the anti-clockwise. So which one causes the beam to rotate away from the ramp would be 45 multiplied by 2.9. Okay, 1.1 plus 3.0 plus 1.5, 45. Measure from point A. Okay, no more already. The other one that causes it to rotate towards the ground, that would be T multiplied by 1.8 plus 96 sine 38 or 59 multiplied by 1.5. Very nice. And then you will get T as 23 Newton. Done. So this one, I tell you what, got top, it's very easy one. You randomly go and find one of these lah. This or this or this is already C1 mark. You never put together in the equation, you get 1 mark already. You put them together in the equation, clockwise is counterclockwise. You didn't misassign the direction. It's another C1. You get the final answer is A1. 3 marks. Very easy. If you totally don't know how to analyze, just find one correct torque and multiply. Force times perpendicular distance. Then you'll be right. Okay? So paper 2 has a lot of kinematics question. It can be up to half of the paper or 40% of the paper. So don't take it for granted. Go and try out the questions. If you don't know, then if you know, then it's very good, right? It's like a nice little relief from circuits. I don't know. Everyone have their preference. Please know your strength and target them. Okay, so that's it for ON22 and ON21. You can see the paper 2 questions are quite manageable. So hopefully that is helpful to you. I'm going to go back to my giant conspiracy drawing. Everything is related to velocity. Okay, and then I'm going to suggest different questions to do. If you want to print out of this map, you can find it in the description box, in the chat box. Cannot find, you pop me a message, let me know. Okay, so now anybody still around? Wow, got 5 people here. Hello. Okay, so, including me. I'm going to start assigning questions. If you later you only want to come and see also can, or stay here also can. I'll focus more on paper 2 lah, okay? Paper 1, you just go and mass spam the questions. 1 is a bit okay. So suggest okay lah, I will take from the recent ones, the more recent ones, okay? Okay, so for uniform motion, which color should I use now? I'm going to use blue. Okay. For uniform motion, ON19 paper 21 question 2. By equation ones lah. Including, okay, projectile, I'll write here. This projectile also needs a bit of practice. Projectile very seldom come out in paper 1. They tend to come out in paper 2. I don't know why. The paper 2-1 variant came out in your trial, I think. I think lah. I am not sure anymore. Should have done before one, but you know, if you haven't, go do. Plenty of projectile in 2018. Okay, good enough. These are all projectile questions. Okay, the ON19 one is free fall. Go and try the overtake question if you haven't do that yet. Look, if you have done it already, then jump straight to model paper, okay? Don't need to stay here. I just want to encourage people to go and spam more projectile question. Okay, I think this one is enough. Time to go for some rebound. Rebound. Overtake. This one is just classic free fall. Classic one. Paper 2-1, question 2. There's another rebound with a twist, which is where we have that girl on the trampoline. Okay, now this is good enough. May, June 13, paper 2-3. So these are all the kinematics questions that you should try. At least some of them, if not all of them. Rebound, but trampoline. Okay. That's all now. What about non-uniform air resistant ones? Okay, non-uniform air resistant ones. ON15 paper 2-3 question 3. Yeah, very quite a few actually, this one. Then we have, actually I think May June 20 also got but I don't think I included it in the handout. ON22 paper 22 question 1 and May June 11 paper 22 question 2. I think this should be good enough. But in case you need it, I also probably discuss one in the examples. ON12 paper 2-1 question 1. This one you understand you are good now. Okay, so that is the kinematics suggested things to try. Moving on to collisions. Okay. So where should I write this? I'm going to write this here. Okay, so collisions. Try out the ON11 paper 2-1 is the rebound plus wall collision. Then I actually think that May June 18 paper 2-3 rebound plus ceiling. FM 19 paper 2-2 2D collision. Oh wait, I never say question number. How smart. It's question 3, rebound plus ceiling. The other one is question 3 as well. And this 12 paper 2-2 is question 3 too. Oh yeah, they're all question 3 lah. Okay, also sketching ON19 paper 22 question 3. The graph. Make sure you know how to draw graphs like this. Okay. This two is graph. May, June 19, paper 21, question 2. But the last one came out in one of your tests before. And then if you want a question about relative speed, ON18, paper 21, question 2. Relative speeds. Okay, this is for collision. Right, what else? This part here. Change in momentum. The momentum is change in mass was strangely popular. ON18 paper 22 question 3. ON18 paper 23 question 3. Go try these two. This F equal MA1 is so common that I don't think I need to specify any example. I think you will have encountered it somewhere along the way by this point now. Okay. When it comes to third law consideration, if you want to use collision and think about a third law consideration, I will also include this question. May, June 17, paper 23, question 2, Newton's third law. Okay, this is more than enough collisions. I think we are good. Let's move on to chapter 5. Okay, we have done quite a lot of equilibrium in ON20, so I think you know how to find equilibrium questions lah. If I see anything interesting, I will point it out. But I don't think there are any. Okay. So you scroll around, you find some equilibrium question, you are okay. But I want to focus on when your net torque is not zero and when you have weird equilibrium questions. So ON14 paper 23 question 3. Got some angle change one. May, June 14 paper 22 question 3. Inclined plane. Change theta. This one got inclined plane. Depending on your appetite and whether you have mastered the inclined plane, don't know lah. Okay, ON13, paper 21, question 4. Couple. Torque on a couple. Okay, and if you have not tried this slightly interesting rebound plus equilibrium question, go try. Go try. Okay, I think that's it for equilibrium. The rest feels very generic. Okay, what else? What else? No question one. Chapter 5. The water pressure one a bit rare lah. If you want to find this, the exact question that I'm talking about, the one where you dip an equilibrium one, this one is May, June 17, paper 21, question 3. Upthrust plus equilibrium. Okay, no more now. Scroll around lah. The rest are pretty straightforward. Pressure, they're okay. All right, work energy power. Work energy power there, normally we will ask with kinematics because it is nicer to ask with kinematics. At least I think it's nicer. I also think that because the variety is very different, you should do more questions from chapter 6 lah, because you can see how they tie things together. But here are some slightly more interesting ones. There is the Feb March 20 paper 22, the one where they talk about young modulus and skier. Is there a young modulus? Some stress strain one. Correct lah. And someone skiing. Okay. ON19 paper 23 question 4. What is this question? Question 3. Question 4. This one is Collision and spring. How interesting. Okay, go do. ON19, paper 2-1, question 4. Spring and KE. Very similar to the ball, but not identical. Okay. You can do May, June 19, paper 2-3. Basically, I'm looking at the more recent questions. Question 2. Projectile and energy. KE, GPE. Well, I think, okay, we did KE. There's a lot of springs here. The glider question is not bad. They're not hard, they're just very different, that's all. Glider got friction one, I think. Air resistance, you glide ma, where got glider, no friction one. I also should bring in an inclined plane. Okay, let's do a double inclined plane. May, June 16, paper 2-2, question 1. 2 times inclined plane. It may seem like a lot of questions, but you are working for 50 marks-ish. So just bear that in mind. I need to find one that has some form of efficiency or power one. This one, ON14, paper 2-1, question 5. Motor and GPE. Motor lah mainly. Okay lah, I think we're okay. The truck one. Sometimes when I show students this truck question, and they're like, oh, I did before, but I don't know why exam cannot do. There. I include here again. Don't know why. May, June 2-1, paper 2-1, question 2. Okay, motor, efficiency, power, and all that lah, plus inclined plane. Okay, so because of how everything can be tied to speed, and speed can be tied to work done, it's like a buffet for them, okay? They can take whatever they want, and then they can just connect any of these questions together. So go use the link to make sure you see the relationship or understand the main idea. Depends how your brain thinks. My brain sees kinematics this way one. Everything is linked because I'm used to it because I've been doing this for many, many years. But when I was a student, it was hard for me to see the connection. Okay. But generally, we are talking about how if let's say there's a change in velocity, we know that there's an acceleration, and based on acceleration, we can find stuff like displacement, time taken to fall, etc., etc. But because there's a change in velocity, there's also a change in momentum, and here leads to an entire can of worms or entire chapter on forces. And because there's change in velocity, there's also work done. And there would be another perspective to look at motion, which is kinematics, dynamics, and work energy power, which is mechanics in a nutshell. 4 chapters, 50 marks. Go try questions. And I will see you in the AMA if you got questions for me. Because I give you so many questions. Maybe you got questions for me. Okay. This is very important in physics lah. That's why they put so much emphasis. Alright.